Long before humanity built telescopes or wrote equations, gravity was already quietly at work, shaping every moment of existence in the universe. It is the invisible thread that gently pulls everything toward everything else, a force so subtle in daily life that we almost forget it exists, and yet so powerful that it binds together stars, galaxies, and entire cosmic structures stretching across billions of light years. Imagine drifting slowly in the quiet darkness of space, surrounded by distant stars glowing softly like tiny lanterns scattered across an endless ocean of black. In that peaceful cosmic silence, gravity is always there, patiently guiding the motion of every object, from the smallest grains of cosmic dust to the largest spiral galaxies. Even here on Earth, as you sit comfortably listening to this story, gravity is gently holding you in place, pressing your feet toward the ground, keeping the oceans in their basins and the atmosphere wrapped softly around the planet like a protective blanket. Without gravity, nothing would stay together. Mountains would not rise, rivers would not flow, and even the air we breathe would drift away into the emptiness of space. The story of gravity begins almost as soon as the universe itself begins. Nearly 14 billion years ago, in the brief moment after the Big Bang, the universe was an incredibly hot, dense sea of energy and particles expanding rapidly in every direction. At first, everything was chaotic and bright, particles rushing outward like sparks from a cosmic fire. But as the universe slowly cooled, gravity began to take on its quiet role as a cosmic organizer. Tiny variations in density appeared within the expanding clouds of matter, and gravity gently amplified those differences, pulling matter together into slightly thicker regions. Over millions of years, those faint clumps slowly grew larger, gathering gas and dust like snowflakes collecting in a winter storm. These early structures would eventually become the first stars and galaxies, glowing islands of light forming within the vast darkness of space. If you could travel back to witness those early moments, the view would be both silent and mesmerizing. Enormous clouds of hydrogen gas would drift slowly through the young universe, their shapes illuminated by the faint glow of newly forming stars. Gravity would pull these clouds inward, compressing them gradually until their centers became hot enough to ignite nuclear fusion. When that happened, the first stars would burst into life, shining brightly against the surrounding darkness. Each of these stars was born because gravity gently persuaded matter to come together, transforming simple clouds of gas into brilliant cosmic furnaces. Gravity does not act like a sudden push or a violent explosion. Instead, it works with incredible patience, pulling objects together slowly, almost tenderly, over vast stretches of time. A single grain of sand has gravity. A mountain has gravity. Even your own body exerts a tiny gravitational pull on everything around it. Of course, these small forces are far too weak for us to notice in everyday life. But when enormous amounts of mass gather together, gravity becomes a powerful architect of the cosmos. Planets orbit stars because gravity keeps them moving along curved paths through space. Moons circle planets for the same reason. Even entire galaxies spin gracefully because gravity binds billions of stars together in vast rotating structures. One of the most comforting aspects of gravity is its reliability. It never turns off, never grows tired, and never forgets its task. Every falling leaf, every rolling ocean wave, every drifting cloud in the sky is quietly guided by gravity's gentle influence. When rain falls from the clouds, gravity guides each droplet downward toward the ground. When a river flows toward the sea, gravity helps pull the water along its winding path. These everyday motions may seem ordinary, but they are all small expressions of the same cosmic force that shapes galaxies and steers planets across the universe. Perhaps the most fascinating thing about gravity is that we cannot actually see it. Unlike light, which travels through space and enters our eyes, gravity is invisible. We only notice its effects through the motion of objects. When an apple falls from a tree, when the moon circles the Earth, or when distant stars orbit the center of a galaxy, we are witnessing gravity at work. For centuries, humans wondered what mysterious force caused these motions. Ancient philosophers proposed ideas ranging from invisible spirits to natural tendencies of matter, but it was not until the 17th century that a clear explanation began to emerge. One quiet afternoon in England, a young scientist named Isaac Newton was sitting beneath an apple tree when he began thinking deeply about why objects fall toward the ground. The falling apple did not strike him on the head as the famous legend suggests, but it did inspire a powerful question. If gravity pulls apples toward Earth, Newton wondered, could the same force also reach all the way to the moon? Could gravity be the reason the moon stays in orbit around our planet? After years of careful thinking and mathematical work, Newton realized that gravity is a universal force acting between every pair of objects in the universe. His discovery changed the way humanity understood motion, revealing that the same simple rule governs both falling apples and the graceful dance of planets around the sun. Yet even Newton's explanation, as revolutionary as it was, turned out to be only part of the story. Centuries later, another scientist would look deeper into the nature of gravity and discover something even more surprising. According to this new understanding, gravity is not simply a force pulling objects together. Instead, it is a bending of space itself, a gentle curve in the fabric of the universe that guides the motion of planets, stars, and galaxies. But that remarkable idea belongs to a later chapter in our story. For now, as we slowly drift deeper into the calm exploration of gravity, imagine again the quiet vastness of space. Stars glow softly in the distance, galaxies swirl like luminous whirlpools, and invisible currents of gravity guide the motion of everything. Though we cannot see it directly, gravity is always there, weaving together the grand cosmic tapestry that makes the universe a place of structure, motion, and quiet beauty. And as our journey continues, we will discover that gravity does far more than simply pull objects downward. It shapes the oceans, guides the moon, controls the tides, builds stars, and even bends the path of light itself. In the next part of our story, we will slowly explore how gravity first began shaping the early universe, turning chaos into order and darkness into the glowing galaxies we see today. In the quiet ages after the universe was born, long before planets or galaxies existed, space was filled mostly with vast clouds of simple elements drifting slowly through the darkness. Hydrogen and helium, the lightest atoms in existence, floated gently across enormous distances like mist spreading across an endless cosmic ocean. The universe at that time was a calm and mysterious place, dimly lit by faint afterglow radiation left behind from the Big Bang. There were no stars yet, no brilliant points of light to pierce the darkness. Instead, there was only an immense, silent expanse filled with invisible motion, where gravity was already beginning its slow and patient work. Imagine drifting through this early universe, surrounded by enormous clouds of gas stretching for millions of kilometers, glowing faintly with soft bluish light. Everything seems peaceful, almost still, yet gravity is quietly guiding the future of the cosmos. Even though gravity is the weakest of nature's fundamental forces, its influence becomes powerful when large amounts of matter gather together. In the early universe, tiny differences in density began to appear within those enormous hydrogen clouds. Some regions held just a little more gas than others. At first, these differences were incredibly small, almost impossible to notice. But gravity has an extraordinary ability to amplify even the smallest imbalance. Wherever a region of gas became slightly denser than its surroundings, gravity began pulling nearby matter toward it, slowly gathering more and more material into the same place. This process happened gradually over millions of years, almost like snowflakes quietly collecting into deeper layers during a peaceful winter night. As gravity continued to pull gas inward, the growing clouds began to collapse under their own weight. The material drifted closer together, forming massive spherical structures called protostellar clouds. Inside these clouds, the gas particles began bumping into each other more frequently as they were squeezed into smaller and smaller spaces. Each collision produced a tiny amount of heat, and over time the centers of these collapsing clouds became warmer and brighter. If you could witness this transformation from afar, you would see enormous glowing clouds slowly swirling inward, their shapes twisting and folding like cosmic storms unfolding in silence. Eventually, deep inside one of these collapsing clouds, the temperature would rise to an astonishing level. When the core reached about 10 million degrees Celsius, something remarkable happened. The hydrogen atoms in the center began fusing together, forming helium and releasing enormous amounts of energy in the process. This moment marked the birth of the first stars in the universe. For the first time since the Big Bang, brilliant points of light ignited across the cosmic darkness, illuminating the vast expanse of space with a warm and steady glow. These first stars were very different from the stars we see today. Because the early universe contained only simple elements like hydrogen and helium, the stars that formed were often much larger and more massive than our sun. Some of them were hundreds of times more massive, burning incredibly hot and bright for relatively short lifetimes. Their light poured across the surrounding space, slowly transforming the universe from a dark and mysterious place into a luminous realm filled with radiance. Gravity played the central role in every step of this process. Without gravity, the clouds of gas would have remained scattered and thin, never gathering together strongly enough to ignite nuclear fusion. Gravity acted like a cosmic sculptor, shaping the raw material of the universe into structures capable of producing light and energy. It guided the swirling motions of gas clouds, controlled their collapse, and created the conditions necessary for stars to shine. As these first stars blazed into existence, they began influencing the surrounding regions of space as well. Their powerful radiation pushed against nearby gas clouds, creating glowing bubbles of heated plasma that expanded slowly outward. Meanwhile, gravity continued its quiet work behind the scenes, pulling together new pockets of gas that would eventually form the next generation of stars. Over time, entire clusters of stars began to appear, scattered like glittering jewels across the growing universe. If you could travel through space during this era, the sight would be both peaceful and breathtaking. Immense star-forming regions would glow softly in shades of gold, blue, and violet, their swirling clouds illuminated by newborn stars hidden within. Gravity would be gently guiding the motion of gas and dust everywhere you looked, orchestrating a slow cosmic ballet that would continue for billions of years. The birth of stars also began changing the chemical makeup of the universe. Inside their blazing cores, stars created heavier elements such as carbon, oxygen, and nitrogen. These elements would later become the building blocks of planets, oceans, and eventually life itself. In this way, gravity did far more than simply pull matter together. By creating stars, gravity helped transform a simple universe made mostly of hydrogen into a rich and complex cosmos filled with diverse structures and materials. Over time, these early stars gathered into larger communities under the influence of gravity. Massive gravitational fields began pulling entire star clusters together, slowly forming the first galaxies. These galaxies would become the enormous stellar cities that populate the universe today, each containing billions or even trillions of stars moving in graceful orbits around invisible centers of gravity. But even while gravity was building these grand structures, it remained invisible and silent. It did not flash or roar like an explosion, nor did it leave behind glowing trails like a comet. Instead, gravity worked patiently across unimaginable spans of time, guiding the motion of matter in a calm and steady way. Its influence was gentle but relentless, shaping the evolution of the cosmos step by step. And so, in the deep quiet of the young universe, gravity became the architect of light. From simple clouds of drifting hydrogen, it created the first stars that would illuminate the cosmic darkness. Those stars would eventually give rise to galaxies, planets, and perhaps even observers like us, quietly contemplating the force that made everything possible. As we continue drifting deeper into this calm exploration, our next chapter will reveal how gravity went even further, gathering countless stars together to form magnificent spiral galaxies that spin slowly through the vast cosmic ocean. As the first stars slowly began to shine across the young universe, gravity continued its quiet work on a much grander scale. The newborn stars did not remain scattered randomly through space for very long. Instead, gravity gently guided them toward one another, drawing thousands and eventually millions of stars into enormous groups that slowly grew larger over time. These gatherings of stars would become the first galaxies, immense cosmic islands floating through the dark ocean of space. If you could drift peacefully through the universe during this ancient era, the view would be breathtaking and calm. Vast clouds of glowing gas would stretch across space like colorful rivers, while clusters of bright young stars would shimmer softly within them. Gravity would be patiently shaping these luminous regions, pulling stars closer together and guiding their motion into graceful patterns that would eventually form the magnificent galaxies we see today. In the early universe, galaxies were not the elegant spiral shapes that modern telescopes often capture. Instead, they began as chaotic and irregular collections of stars and gas, slowly swirling under the influence of gravity. Massive clouds of hydrogen gas continued collapsing to form new stars, while older stars drifted through space like glowing embers in a cosmic fire. Gravity acted as the quiet conductor of this enormous orchestra, guiding every star and every cloud of gas along invisible pathways. Over millions of years, the constant pull of gravity began to organize these chaotic star clusters into larger structures, gradually shaping them into rotating systems. One of the most beautiful outcomes of this slow cosmic process was the formation of spiral galaxies. Imagine an enormous disk of billions of stars slowly spinning through space like a giant celestial whirlpool. At the center of this rotating structure lies a dense, glowing core filled with countless tightly packed stars. Surrounding the core are sweeping spiral arms that curve outward gracefully, each arm filled with bright stars, glowing nebula clouds, and drifting cosmic dust. Gravity holds every part of this structure together, ensuring that the stars move along smooth orbits around the galactic center. The formation of a spiral galaxy is a slow and mesmerizing event that unfolds over billions of years. As gravity gathers matter into a rotating disk, the stars within that disk begin moving in slightly different directions and speeds. Some stars drift inward while others move outward, creating waves of motion within the galactic disk. These waves eventually form the spiral arms we see in many galaxies today. If you could watch this transformation in real time, it would resemble a slow cosmic dance, with stars tracing luminous paths through space as the galaxy gently turns. Not all galaxies become spirals. Gravity sometimes creates other shapes as well. In some regions of the universe, massive clusters of stars collapse into enormous elliptical galaxies, which appear as glowing spheres of starlight rather than flat disks. These galaxies contain trillions of stars packed closely together, moving in many different directions under the influence of gravity. From a distance, they glow like enormous golden lanterns drifting through the darkness of space. Other galaxies form irregular shapes that seem almost chaotic. These irregular galaxies often arise when gravity pulls galaxies toward one another, causing them to interact and sometimes even collide. Although the word collision might sound violent, these galactic encounters unfold very slowly over millions of years. When two galaxies pass near each other, their gravitational fields begin pulling at one another like invisible tides. Streams of stars may stretch outward into long glowing arcs, while enormous clouds of gas collide and ignite bursts of new star formation. The result can be an incredibly beautiful and dynamic structure, glowing with newly formed stars and swirling gas clouds. Gravity ensures that galaxies rarely exist alone. Across the universe, galaxies gather together into enormous groups known as galaxy clusters. Some clusters contain hundreds or even thousands of galaxies, all moving slowly within a shared gravitational field. If you could observe such a cluster from afar, it might look like a vast swarm of glowing islands drifting together in the darkness of space. Each galaxy spins quietly within the cluster, while gravity binds the entire structure into a stable cosmic community. Between these galaxies lies an immense region of nearly empty space, yet even here gravity continues to exert its influence. The gravitational pull of massive galaxy clusters can bend the path of light traveling through space, creating strange visual effects where distant galaxies appear stretched or curved like reflections in a funhouse mirror. Although we will explore this fascinating phenomenon later in our journey, it serves as another reminder that gravity shapes not only the motion of matter but even the path of light itself. Perhaps one of the most astonishing aspects of galaxies is their scale. Our own galaxy, the Milky Way, contains hundreds of billions of stars, each one held in orbit around the galactic center by gravity. If you could travel from one side of the Milky Way to the other at the speed of light, the journey would still take more than 100,000 years. And yet this enormous structure remains stable and organized because gravity carefully balances the motion of all its stars. Within the spiral arms of galaxies, new stars are constantly forming. Giant clouds of gas drift slowly through these regions, and gravity once again gathers the material together to create fresh generations of stars. In this way, galaxies become cosmic nurseries where gravity repeatedly transforms simple gas into glowing stellar systems. Some of these stars will eventually develop planetary systems, and on certain rare planets, conditions may arise that allow life to emerge. It is remarkable to think that gravity, a force we experience every moment without noticing, is responsible for building structures so vast and magnificent. From the gentle fall of a raindrop on Earth to the swirling motion of entire galaxies, gravity connects every scale of the universe through the same quiet influence. As we continue drifting through this calm cosmic story, imagine yourself floating far beyond our galaxy, gazing across a landscape filled with countless galaxies glowing softly in the darkness. Each one spins slowly, guided by gravity, forming part of a vast cosmic web that stretches across the universe. Invisible threads of gravitational attraction link these galaxies together, creating one of the largest structures known to science. In the next part of our journey, we will bring our focus closer to home and explore how gravity keeps planets moving in stable paths around their stars. This delicate balance between motion and attraction is what allows worlds like Earth to exist in peaceful orbits, traveling through space year after year in a gentle cosmic rhythm. As galaxies slowly formed and filled the universe with shining stars, gravity continued shaping smaller and more delicate systems within them. Around many stars, swirling disks of gas and dust began forming, glowing softly in the quiet darkness of space. These disks, known as protoplanetary disks, were the birthplaces of planets. Within these enormous rings of drifting material, tiny grains of dust gently collided and stuck together, forming larger and larger clumps over time. Gravity quietly guided this process, pulling particles closer and helping them gather into growing bodies that would eventually become planets. If you could observe one of these early systems from afar, the scene would appear peaceful and mesmerizing. A young star would glow warmly at the center, surrounded by a vast rotating disk filled with shimmering dust and gas slowly circling in graceful motion. Over thousands and eventually millions of years, the dust particles within this disk began forming larger objects called planetesimals. These rocky bodies continued colliding and merging, slowly building into worlds that grew larger and heavier as gravity pulled more material toward them. Some of these growing planets gathered thick atmospheres of gas, becoming enormous giants like Jupiter or Saturn, while others remained smaller and rocky like Earth or Mars. But as these planets formed, another remarkable phenomenon began shaping their motion. Instead of falling directly into their parent star, the planets began traveling in smooth, curved paths known as orbits. The reason planets stay in orbit rather than simply crashing into their stars lies in a beautiful balance between motion and gravity. Imagine throwing a stone across a calm lake. The stone travels forward through the air because of the speed given by your throw, while gravity pulls it downward toward the water. If the stone were thrown gently, it would quickly fall into the lake. But if it could somehow travel forward fast enough while still being pulled downward, it would continue curving around the lake instead of falling straight down. In space, something similar happens on a much larger scale. When planets formed within the swirling disk around a star, they already possessed motion, moving sideways through space as part of the rotating disk. Gravity from the star pulled them inward, but their sideways motion prevented them from falling directly into the star. This delicate balance created stable orbits, where planets continuously fall toward their star but always miss it because of their forward motion. The result is a graceful cosmic dance where planets circle their stars again and again, sometimes for billions of years. If you could watch one of these planetary systems from a distance, the movement would appear calm and rhythmic. Each planet would follow its own path around the star, some moving quickly along tight inner orbits, while others drift slowly along wider paths farther away. Our own solar system is a perfect example of this quiet balance. At its center shines the Sun, a glowing sphere of hot plasma whose immense gravity holds the entire system together. Around the Sun orbit 8 major planets, along with countless moons, asteroids, and comets. Each one follows its own path through space, guided by gravity and its own motion. Mercury, the closest planet to the Sun, moves quickly along a tight orbit, completing a full journey in just 88 days. Earth, our home planet, takes about 1 year to complete its orbit, traveling through space at an incredible speed of roughly 30 kilometers per second. Yet despite this tremendous speed, the motion feels perfectly stable because gravity constantly pulls Earth toward the Sun while its forward motion keeps it moving along a curved path. This elegant balance between gravity and motion allows planets to remain in stable orbits for billions of years. Without gravity, planets would simply drift away into deep space, leaving their stars behind. Without motion, they would fall straight into their stars and disappear. But together, these two factors create the gentle, predictable paths that define planetary systems throughout the universe. Gravity also plays an important role in shaping the structure of these systems over time. Large planets exert gravitational influence on smaller bodies nearby, sometimes pulling them into new orbits or ejecting them entirely from the system. Asteroids drifting too close to a giant planet may be captured as moons, while others may be flung outward into distant regions of space. Even comets, those icy wanderers that occasionally visit the inner solar system, are guided along long looping orbits by the combined gravitational pull of the Sun and the planets. Moons themselves follow the same principles of orbital motion. Just as planets orbit stars, moons orbit planets, held in place by gravity while moving forward through space. Our own moon circles Earth in a steady rhythm, completing one orbit approximately every 27 days. As it travels along this path, gravity keeps it bound to our planet, preventing it from drifting away into the darkness of space. If you could view the solar system from far above its plane, the sight would resemble a vast celestial clockwork. The Sun would glow at the center, while planets trace luminous circles around it, each moving at its own pace. Smaller objects would drift between these orbits, sometimes crossing paths or forming rings of scattered debris. All of these motions are guided by gravity, which ensures that the system remains stable and organized despite its immense size. Even tiny changes in gravity can influence these motions over long periods of time. The gravitational interactions between planets slowly shift their orbits in subtle ways, creating complex patterns that astronomers continue to study. These slow changes occur over millions of years, gradually reshaping the architecture of planetary systems. Yet despite all this complexity, the basic idea remains beautifully simple. Planets stay in orbit because they are always falling toward their star while simultaneously moving forward through space. This continuous falling creates the curved paths that keep them circling their star rather than crashing into it. As we continue drifting through our peaceful exploration of gravity, it becomes clear that this invisible force is responsible for the stability of entire planetary systems. It allows stars to hold onto their planets, planets to hold onto their moons, and galaxies to hold onto their stars. Everywhere we look in the universe, gravity quietly maintains this delicate balance. In the next chapter of our story, we will bring our journey even closer to home and explore how gravity shapes life here on Earth, guiding the flow of rivers, the movement of oceans, and the gentle falling of rain from the sky. As our journey through the quiet wonders of gravity continues, we slowly return from the immense scales of galaxies and planetary systems to a place much closer to home. Here on Earth, gravity is always present, shaping nearly every motion we see around us. Yet because it is so familiar, we rarely stop to notice it. The gentle pull that keeps your feet resting on the ground, the falling motion of rain drifting from clouds, and the steady flow of rivers toward the sea are all guided by the same invisible force that governs the motion of stars across the universe. Gravity connects the largest cosmic structures to the smallest everyday experiences, quietly linking our world to the grand architecture of the cosmos. Imagine standing on a peaceful shoreline during the early evening as the sky glows with soft shades of orange and violet. The ocean stretches out before you, its surface rising and falling slowly in long rolling waves. Each wave moves toward the shore, guided by wind and currents, but beneath all of these motions lies gravity, patiently holding the vast mass of the ocean against the surface of the Earth. Without gravity, the oceans would not remain here at all. Water would drift freely into space, forming clouds of vapor far from the planet. Instead, gravity gently presses the oceans toward the Earth's center, keeping them gathered in vast basins that cover most of the planet's surface. Gravity also gives water its natural tendency to flow downward. When rain falls high in the mountains, tiny streams begin forming among rocks and soil. These small streams join together, gradually becoming larger rivers that wind their way through valleys and forests. No matter how long or complex the journey becomes, the water is always guided by gravity, slowly descending toward the lowest points of the landscape. Eventually, these rivers reach the oceans, completing a quiet and continuous cycle that has shaped the surface of the Earth for millions of years. If you could watch the movement of water across the planet from high above, the view would be peaceful and mesmerizing. Countless rivers would appear like shimmering threads weaving through the land, all slowly flowing toward the seas. Snow melting in distant mountains would begin its long journey downward, guided by gravity along twisting paths carved into the landscape. Even underground, water moves quietly through hidden channels and porous rock layers, always drifting in the direction gravity encourages. Gravity does more than guide the movement of water, it also shapes the very surface of the Earth itself. Mountains slowly erode as rocks break apart and tumble downward along steep slopes. Landslides occasionally occur when gravity pulls loose soil and stone toward the valley below. Over long stretches of time, these slow downward movements reshape the land, carving valleys, forming plains, and smoothing the jagged edges of ancient mountains. Even the air around us is held in place by gravity. Earth's atmosphere is a delicate blanket of gases that surrounds the planet, extending hundreds of kilometers into space. Gravity gently pulls these gases toward the planet's surface, keeping them from drifting away into the vacuum of space. This atmospheric blanket protects life from harmful radiation, regulates temperature, and provides the oxygen we breathe. Without gravity, the atmosphere would slowly escape into space, leaving the planet barren and silent like many worlds in our solar system. When you take a quiet breath, gravity is already playing a role in that simple action. The air around you remains close to Earth's surface because gravity holds it there. Warm air rises while cooler air sinks, creating gentle atmospheric currents that shape weather patterns across the planet. Clouds form when rising air cools and water vapor condenses into tiny droplets, and when those droplets grow large enough, gravity draws them downward as rain. Rain itself is a beautiful expression of gravity's influence. High above the Earth, clouds gather moisture from evaporating oceans and lakes. Tiny droplets slowly merge into larger ones as they drift within the cloud. Eventually, the droplets become heavy enough that gravity begins pulling them downward. From the ground, this moment appears as a peaceful rainfall, with countless droplets drifting gently through the air toward the surface below. Gravity also influences the movement of the oceans on a much larger scale. The weight of the water presses downward toward the center of the Earth, creating immense pressure in the deep ocean trenches thousands of meters below the surface. At the same time, Earth's rotation and the shape of the planet cause the oceans to form a slightly bulging shape around the equator. This subtle effect arises because the spinning motion of the planet works alongside gravity to shape the distribution of water across its surface. Even the act of walking across the ground depends entirely on gravity. Each step we take pushes against the Earth's surface, and gravity pulls us back toward it, allowing us to remain balanced as we move. Without gravity, even the simplest movements would become difficult and unfamiliar. Astronauts who experience weightlessness in space often describe how strange it feels to move without the constant pull of gravity guiding their bodies. Despite how essential gravity is to life on Earth, its strength here is actually quite gentle compared to many other places in the universe. Giant planets like Jupiter possess far stronger gravitational fields, capable of pulling objects downward with tremendous force. On the other hand, small moons and asteroids have much weaker gravity, allowing objects to float easily above their surfaces. Here on Earth, gravity strikes a delicate balance that allows oceans to remain liquid, air to stay close to the surface, and living creatures to move comfortably across the land. This balance has played a crucial role in making our planet a stable and welcoming environment for life to flourish. As the evening grows quiet and the sound of distant waves drifts across the shoreline, it becomes clear that gravity is more than just a scientific concept. It is a quiet companion that shapes every landscape, every river, and every falling raindrop. It is the gentle force that keeps the oceans where they belong and allows life to thrive on this remarkable world. In the next part of our journey, we will explore how gravity interacts with the moon to create the rhythmic rise and fall of the ocean tides, a graceful dance between Earth and its closest celestial companion. As the Earth slowly turns beneath the vast sky, another celestial companion quietly circles our planet, guiding rhythms that humans have observed for thousands of years. High above the oceans, drifting silently through the darkness of space, the moon follows its steady orbit around Earth. Its pale glow often lights the night with a calm silver radiance, but beyond its beauty, the moon is deeply connected to the invisible force of gravity that shapes our world. Together, Earth and the moon perform a slow cosmic dance, and one of the most peaceful and fascinating results of this relationship is the gentle rise and fall of the ocean tides. Imagine standing again beside the ocean during a quiet night. The sky is dark and filled with distant stars, while the moon hangs softly above the horizon, casting a pale reflection across the water. The sea appears calm, yet over the course of the night the shoreline will slowly change. Water will gradually creep farther onto the beach, reaching places that were dry only hours before. Later, the ocean will quietly retreat again, revealing wet sand glistening under the moonlight. This steady breathing motion of the oceans is known as the tides, and gravity is the quiet force guiding every moment of it. At first glance, it might seem simple to imagine that the moon's gravity simply pulls the ocean upward, causing the water beneath it to rise. In reality, the process is slightly more complex and far more fascinating. The moon's gravity pulls on the entire Earth, including both the solid land and the vast oceans. However, because water flows freely, the oceans respond more visibly to this gravitational pull than the solid ground beneath them. On the side of Earth facing the moon's gravity gently draws ocean water toward it, creating a subtle bulge of water that stretches outward toward the moon. At the same time, something surprising happens on the opposite side of the planet. There, another bulge forms as well, caused by the difference in gravitational pull between the near side and the far side of the Earth. The result is that Earth actually carries two tidal bulges, one facing the moon and one on the opposite side. As Earth slowly rotates once every 24 hours, different parts of the planet pass through these bulges of ocean water. This is why most coastlines experience two high tides and two low tides each day. From the perspective of someone standing on the shore, the ocean appears to slowly rise and fall as the planet turns beneath these gentle gravitational swells. The movement of tides is slow and calm, perfectly suited to the quiet rhythm of the natural world. It can take several hours for the tide to fully rise or fall, creating a gradual transformation of the shoreline. Beaches that were wide and dry during low tide may become narrow as the water slowly advances. Rocks hidden beneath the waves may appear briefly before being submerged again when the tide returns. Over long periods of time, tides have shaped coastlines around the world. The constant movement of water erodes cliffs, carries sand along beaches, and forms complex ecosystems in tidal zones. In many places, unique habitats exist where land and sea meet, supporting plants and animals that have adapted to the changing rhythm of the tides. The moon is not the only celestial body influencing Earth's tides. The sun, though far more distant, also exerts its own gravitational pull on the oceans. When the sun, moon, and Earth align in a straight line during the full moon or new moon, their combined gravitational forces create especially strong tides known as spring tides. During these times, the difference between high tide and low tide becomes greater, and the ocean's movement becomes more dramatic. At other times, when the sun and moon form a right angle relative to Earth, their gravitational pulls partially cancel each other out. This produces weaker tides known as neap tides, where the difference between high and low water levels is smaller. These variations add another layer of rhythm to the ocean's movement, creating a repeating cycle that follows the phases of the moon throughout each month. If you could watch Earth from space during this process, the movement of the tides would appear like two enormous waves slowly traveling across the surface of the planet. As Earth rotates beneath them, continents pass through these bulges of water, experiencing the rising and falling of the sea as part of a continuous planetary rhythm. Beyond shaping the oceans, the gravitational connection between Earth and the Moon has influenced the planet in other subtle ways as well. The tides create friction as ocean water moves across the seafloor, and this friction gradually slows Earth's rotation by a tiny amount over extremely long periods of time. As a result, days on Earth have become slightly longer over billions of years. The Moon itself is also slowly drifting farther away from Earth at a rate of a few centimeters each year, a consequence of the same tidal interactions between the two bodies. Though this change is incredibly slow, it reminds us that gravity is constantly shaping the evolution of planetary systems, even on timescales far longer than human history. For ancient civilizations, the tides were mysterious forces that seemed to follow the moon through the sky. Sailors and coastal communities learned to observe these patterns carefully, using them to guide navigation, fishing, and travel along the sea. Today, modern science allows us to understand the gravitational mechanics behind these movements, yet the tides remain just as calming and beautiful as they were to people centuries ago. Standing beside the ocean at night, watching the slow rise of the tide beneath the glow of the moon, it is easy to feel the quiet harmony between our planet and its celestial companion. Gravity connects them in a silent relationship that continues day after day, year after year, guiding the oceans through their endless cycle of motion. And as our peaceful journey through gravity continues, we will soon explore how humans have learned to overcome this force, building powerful machines that allow us to escape Earth's gravitational pull and travel into the vastness of space beyond. As we continue drifting through the peaceful story of gravity, it becomes clear that this invisible force holds our entire world gently in place. Everything on Earth, oceans, mountains, clouds, animals, and people, is quietly pulled toward the planet's center. Gravity keeps our atmosphere from floating away and ensures that every step we take returns us safely to the ground. Yet for centuries, humans have wondered what it might feel like to leave this constant pull behind and travel beyond the sky. The idea of escaping Earth's gravity once seemed like an impossible dream, something that existed only in imagination and stories about journeys to the stars. For most of human history, the sky appeared unreachable. Birds could soar high above the ground, and clouds drifted across the atmosphere, but the vast darkness beyond them remained distant and mysterious. Gravity held everything firmly on Earth, and no natural process seemed capable of lifting humans high enough to escape its grasp. Even the tallest mountains reached only a tiny fraction of the distance required to leave the planet behind. But gravity, while powerful, follows clear and predictable laws. Over time, scientists began to understand how objects move when they are pushed upward against Earth's gravitational pull. When a stone is tossed into the air, it rises briefly before gravity slows it down and pulls it back toward the ground. The faster the stone is thrown, the higher it travels before gravity brings it back. From this simple observation came a remarkable realization. If something could be launched fast enough, it might continue moving forward while falling toward Earth, creating an orbit rather than returning to the ground. To truly escape Earth's gravity, however, an object must reach an extraordinary speed known as escape velocity. This speed is about 11 kilometers per second, which means traveling fast enough to cover the distance of an entire city in less than a second. Achieving such speed requires enormous amounts of energy, far more than any simple machine could provide. This challenge eventually led to the invention of rockets, powerful engines designed to push themselves upward by expelling hot gases downward at tremendous speed. The principle behind a rocket is surprisingly simple. When gas shoots out in one direction, the rocket itself moves in the opposite direction. By continuously pushing exhaust downward, a rocket generates enough thrust to climb upward through the atmosphere, fighting against the pull of gravity every moment. Imagine standing far from a launch site on a quiet morning just before a rocket lifts off. The sky above is calm and blue, and the rocket stands tall on its platform like a slender tower pointing toward space. When the engines ignite, an immense burst of flame and smoke erupts beneath the rocket, and a powerful roar fills the air. Slowly at first, the rocket begins rising upward, pushing against Earth's gravity with steady determination. During the first part of its journey, the rocket must overcome the thick layers of Earth's atmosphere as well as gravity itself. The engines burn enormous quantities of fuel, producing a continuous stream of thrust that lifts the vehicle higher and higher. As it climbs, the sky gradually darkens from bright blue to deep violet and eventually to the blackness of space. Even as the rocket rises, gravity never disappears. Instead, it continues pulling the rocket downward, trying to bring it back to Earth. The rocket must keep accelerating until it reaches the speed required to remain in orbit or escape completely. If it reaches orbital speed, it will begin circling Earth much like the Moon does, constantly falling toward the planet but moving forward fast enough to keep missing it. Astronauts traveling aboard such spacecraft often describe a remarkable sensation once the rocket reaches orbit. Inside the spacecraft, objects begin floating gently through the air, and the astronauts themselves drift weightlessly around the cabin. This feeling is known as microgravity, but it does not mean that gravity has vanished. In fact, gravity is still pulling on the spacecraft and everything inside it. The reason astronauts float is because the spacecraft and its occupants are all falling toward Earth together while moving forward at tremendous speed. Since everything is falling at the same rate, there is no feeling of weight pressing objects downward. Instead, everything inside the spacecraft floats freely, creating the peaceful sensation of weightlessness. If you could observe Earth from the window of an orbiting spacecraft, the view would be both breathtaking and calming. The curved surface of the planet would stretch below, covered in swirling clouds and deep blue oceans. Continents would drift slowly beneath the spacecraft as it circled the planet every 90 minutes or so. From this height, gravity would still be holding the spacecraft in its path, guiding it smoothly around the Earth. Some spacecraft travel even farther, escaping Earth's gravitational pull entirely and venturing deeper into the solar system. These missions require even greater speeds and carefully planned trajectories that use the gravity of planets to gain additional momentum. In a process called gravitational assist, a spacecraft can swing past a planet and use its gravity to accelerate, much like a slingshot sending a stone flying forward. Through these remarkable techniques, human-made spacecraft have visited distant worlds such as Mars, Jupiter, and Saturn. Robotic explorers have traveled billions of kilometers through space, all while navigating the invisible gravitational fields of planets and stars. Yet even as humans venture outward, gravity remains a constant companion. It shapes the paths of spacecraft, guides their journeys, and ultimately determines how they travel through the cosmos. Far from being an obstacle alone, gravity becomes a tool that scientists and engineers use to explore the universe. Looking up at the night sky from Earth, it may seem impossible that we have learned to travel beyond the planet's gravitational hold. But through careful understanding of gravity and motion, humanity has found ways to rise above the surface and drift among the stars. As our gentle exploration continues, the next chapter will take us deeper into one of gravity's most mysterious creations, black holes, places where gravity becomes so powerful that even light itself cannot escape their grasp. As our calm journey through the universe continues, we have seen how gravity gently gathers gas to form stars, organizes galaxies into elegant spirals, and keeps planets moving in peaceful orbits around their suns. Most of the time, gravity acts like a patient sculptor, slowly shaping the universe in graceful and balanced ways. But in some rare places, gravity becomes far more powerful and mysterious. In these regions, matter collapses inward so intensely that space itself bends dramatically, creating one of the most fascinating objects known in modern astronomy, the black hole. To understand how a black hole forms, imagine a massive star many times larger than our Sun. For millions of years, the star shines brightly, producing enormous amounts of energy through nuclear fusion in its core. This fusion process pushes outward, balancing the powerful inward pull of gravity. As long as this balance continues, the star remains stable, glowing peacefully in space. But eventually, even the most massive stars begin to run out of fuel. When the fusion reactions in the core slow down, the outward pressure that once supported the star begins to fade. Gravity, which has been pulling inward the entire time, suddenly becomes the dominant force. Without enough energy pushing outward, the star can no longer support its own enormous weight. At this moment, the core of the star begins collapsing inward under the intense pull of gravity. The collapse happens incredibly fast, compressing matter into an extremely small and dense region. The outer layers of the star may explode outward in a brilliant event known as a supernova, briefly shining brighter than entire galaxies. Yet deep inside the center of this explosion, gravity continues crushing the remaining core into something far smaller and far denser than anything we normally encounter in the universe. If the collapsing core is massive enough, gravity will compress it beyond the limits of ordinary matter. The material shrinks into a region so compact that its gravitational pull becomes extraordinarily strong. Eventually, the escape velocity of this object becomes greater than the speed of light itself. When this happens, not even light can travel fast enough to escape its gravity. The result is a black hole. Despite their dramatic name, black holes are not giant cosmic vacuums that swallow everything nearby. Instead, they behave much like other massive objects, exerting gravity that influences the surrounding space. A black hole can have the mass of several stars, yet all of that mass is compressed into an incredibly small region known as a singularity. Surrounding this mysterious center is a boundary called the event horizon. This invisible surface marks the point of no return. If anything crosses the event horizon, whether it is gas, dust, or even light, it can no longer escape the gravitational pull of the black hole. From the outside, the event horizon appears as a perfectly dark circle because no light can return from beyond it. Yet the regions around black holes can be surprisingly luminous and active. Gas and dust drifting too close to a black hole begins spiraling inward, forming a swirling structure called an accretion disk. As this material spins faster and faster, friction heats it to incredibly high temperatures. The disk begins glowing with intense radiation, sometimes becoming one of the brightest objects in the entire galaxy. If you could observe this scene from a safe distance, the view would be both dramatic and mesmerizing. A glowing disk of blazing gas would circle a dark center where the black hole resides. Jets of energetic particles might shoot outward from the poles, extending for thousands of light years into space. Meanwhile, gravity would be bending the paths of nearby stars and light, creating strange distortions in the surrounding region. One of the most fascinating effects near a black hole is the bending of space and time itself. According to modern physics, gravity does not simply pull objects together. Instead, massive objects bend the fabric of space-time around them. Near a black hole, this bending becomes extremely strong, causing time to slow down relative to distant observers. If someone could safely observe a clock near the edge of a black hole, they would see it ticking more slowly than a clock far away in space. To the observer near the black hole, time would feel perfectly normal, but to someone watching from a distance, the passage of time would appear stretched and slowed. This strange effect reveals just how deeply gravity can influence the universe. Black holes also play an important role in shaping galaxies. At the center of many galaxies lies a supermassive black hole containing millions or even billions of times the mass of the Sun. These enormous objects quietly sit at the heart of their galaxies, influencing the motion of stars that orbit far around them. Our own galaxy, the Milky Way, contains such a supermassive black hole at its center. Although it lies tens of thousands of light years away, astronomers have observed stars orbiting an invisible object there, moving at incredible speeds. From these motions, scientists have concluded that a massive black hole resides in the center of our galaxy, silently anchoring the entire galactic structure. Despite their powerful gravity, black holes are not eternal prisons. Modern physics suggests that over extremely long periods of time, black holes may slowly lose energy through a process known as Hawking radiation. This effect is incredibly subtle, and for most black holes the process would take far longer than the current age of the universe to make any noticeable difference. Even so, The idea that black holes might slowly fade away adds another layer of mystery to these extraordinary objects. They remind us that gravity, though invisible, can shape the universe in ways both gentle and extreme. From the calm motion of tides on Earth to the crushing collapse of massive stars, gravity reveals many different faces throughout the cosmos. It is a force capable of building galaxies, guiding planets, and creating the most powerful gravitational structures we know. As our peaceful exploration continues, we will soon discover how gravity can even bend light itself, allowing massive objects in space to act like natural cosmic lenses that reveal distant parts of the universe. As our slow and peaceful journey through the mysteries of gravity continues, we begin to discover that gravity does far more than simply pull objects toward one another. It does something even more extraordinary. Gravity can bend the very path that light travels through space. This idea may seem surprising at first, because light moves incredibly fast and appears to travel in perfectly straight lines. Yet when light passes near a massive object, gravity gently curves the space around it, and the light follows that curved path. To imagine this, picture space not as empty nothingness, but as a smooth fabric stretching across the universe. When a massive object like a star or galaxy sits on that fabric, it creates a small dip or curve around it. Smaller objects passing nearby will move along the curved surface created by the massive object. In a similar way, beams of light traveling through space will also follow the gentle curves created by gravity. This remarkable effect was first predicted by one of the most influential scientific ideas of the 20th century, the theory of general relativity. According to this theory, gravity does not act as a simple pulling force across empty space. Instead, massive objects change the shape of space itself. Light, which always follows the straightest possible path through space, ends up moving along these curved regions created by gravity. For many years, this concept seemed almost too strange to believe. But careful observations eventually confirmed that gravity truly can bend light. One of the first pieces of evidence came when astronomers noticed that stars appearing close to the sun during a solar eclipse seemed slightly shifted from their normal positions. The sun's gravity was bending the light from those distant stars as it passed near the sun on its way to Earth. Once scientists realized that gravity could bend light, they began to notice this effect throughout the universe. Massive galaxies and clusters of galaxies act like enormous cosmic lenses, bending and focusing light from objects that lie far behind them. This phenomenon is known as gravitational lensing. If you could observe a distant galaxy cluster through a powerful telescope, the view might appear almost magical. Behind the cluster, even more distant galaxies shine faintly across the universe. But as their light passes through the strong gravitational field of the cluster in front, the light bends in several directions. Instead of appearing as simple points of light, those distant galaxies may stretch into long arcs or curved streaks around the cluster. Sometimes the bending is so symmetrical that it forms a complete ring of light surrounding the massive object in the center. These glowing rings, known as Einstein rings, are among the most beautiful sights in modern astronomy. They occur when the distant galaxy, the massive lensing object, and Earth all line up perfectly in space. The beauty of gravitational lensing is not only visual. It also allows astronomers to study parts of the universe that would otherwise be too faint or distant to observe. The bending of light acts like a natural magnifying glass, amplifying the brightness of faraway galaxies and allowing scientists to see objects that formed billions of years ago. In a way, gravity itself becomes a telescope. Massive galaxy clusters spread across the cosmos act as giant lenses, helping astronomers peer deeper into space and further back in time. Some of the most distant galaxies ever discovered have been revealed through this gentle bending of light. Gravitational lensing also helps scientists measure the invisible mass of the universe. Not all matter emits light. Large amounts of mysterious material known as dark matter exist throughout the cosmos, and it cannot be seen directly. However, dark matter still produces gravity. By studying how light bends around galaxies and clusters, astronomers can map where this hidden mass must be located. In many cases, the bending of light reveals that galaxies are surrounded by enormous halos of dark matter extending far beyond the visible stars. These halos quietly shape the motion of galaxies and help hold galaxy clusters together. Without gravitational lensing, much of this invisible structure would remain completely hidden. If you could travel through one of these regions of space where gravity strongly bends light, the view would appear truly unusual. Stars behind a massive object might appear slightly distorted or stretched, almost like reflections in a curved mirror. The sky would seem subtly warped, with light following paths shaped by the gravitational landscape of the surrounding universe. Even black holes, the extreme objects we explored earlier, can bend light dramatically. Near a black hole, the curvature of space becomes so strong that light can loop around the object before escaping. This creates bright rings of light around the black hole, known as photon rings. These rings were part of the stunning images captured by astronomers when they first photographed the shadow of a black hole. Yet despite the dramatic nature of these effects, the bending of light by gravity usually occurs very gently. Most of the time, the curves in space are small and difficult to notice without precise instruments. But across vast cosmic distances, even small bends can create remarkable visual patterns that reveal hidden structures in the universe. Gravity, which once seemed like a simple force pulling objects downward, continues to reveal deeper and more subtle layers of influence. It shapes the motion of galaxies, forms black holes, and even redirects the paths of light traveling across billions of light years. As we drift quietly through this cosmic story, it becomes clear that gravity is not only shaping matter but also shaping how we see the universe itself. Every beam of light arriving at our telescopes carries with it a history of gravitational interactions that occurred during its long journey through space. In the next part of our exploration, we will discover how gravity can also create invisible waves that ripple through the fabric of space and time itself, carrying messages from some of the most dramatic events in the universe. As our gentle journey through gravity continues, we enter one of the most mysterious and peaceful-sounding phenomena in the universe: gravitational waves. These are not waves of water, nor waves of sound traveling through air, but invisible ripples that move through the very fabric of space and time itself. Imagine space as a calm, infinite ocean stretching across the universe. When something powerful and massive disturbs this cosmic ocean, waves begin to spread outward, slowly carrying energy across enormous distances. These waves are so subtle that they pass through Earth every day without us ever noticing, quietly flowing through our bodies, our planet, and everything around us. Gravitational waves were first predicted as part of modern physics when scientists realized that massive objects moving through space could disturb space-time, similar to how a heavy stone dropped into still water creates ripples across a pond. When extremely powerful events happen in the universe, such as two massive stars colliding or black holes merging together, they release enormous amounts of energy. Some of this energy travels outward as gravitational waves, carrying information about the event that created them. For a long time, scientists believed gravitational waves might exist, but they had no way to detect them. The waves are incredibly weak by the time they reach Earth. Even the strongest gravitational waves passing through our planet change distances by amounts far smaller than the width of a single atom. Detecting something so small required extremely sensitive instruments and decades of scientific innovation. If you could watch a gravitational wave traveling through space, the experience would be strangely calming. Instead of seeing light or matter moving, you would notice space itself stretching and squeezing gently as the wave passed. Objects would not move through space. Instead, space would move around them, expanding slightly in one direction while compressing in another. This subtle stretching and compression would continue as the wave traveled outward from its source at the speed of light. The most powerful sources of gravitational waves come from the most dramatic events in the universe. When two black holes orbit each other, they gradually lose energy as they emit gravitational waves. This causes them to spiral closer and closer together over millions of years. At first, the motion is slow and graceful, like two dancers slowly circling each other in space. But as they get closer, their speed increases dramatically, and the gravitational waves they emit grow stronger and stronger. Eventually, the black holes collide in a final dramatic moment. The collision releases an enormous burst of gravitational wave energy, sending powerful ripples across the universe. These ripples can travel for billions of years before reaching distant planets like Earth. When they finally arrive, they are extremely faint but still detectable with advanced scientific instruments. Scientists built special detectors on Earth to observe these waves. These detectors use laser beams traveling through long vacuum tunnels to measure extremely tiny changes in distance caused by passing gravitational waves. When a gravitational wave passes through, it slightly stretches one tunnel while compressing another. By measuring these changes, scientists can confirm that a gravitational wave has traveled through the detector. The first direct detection of gravitational waves marked a major milestone in human understanding of the universe. It confirmed predictions made decades earlier and opened a new way for scientists to study space. Instead of observing only light from distant objects, astronomers could now listen to the invisible vibrations of space-time itself. Gravitational waves also help scientists study events that would otherwise be impossible to observe. Some cosmic events do not produce visible light, especially when black holes collide. Before gravitational wave astronomy, these events were completely hidden from view. Now, scientists can detect them through the subtle ripples they leave behind. If you could float far away in deep space, far from any stars or galaxies, you might think space would be completely still. But even there, gravitational waves would be quietly passing through, stretching and compressing space-time like soft breathing motions of the universe itself. These waves do not disturb matter violently. Instead, they move peacefully through everything, carrying information across cosmic distances. Gravitational waves also help scientists understand the history of the universe. Some waves were created during the earliest moments after the Big Bang, carrying information about the universe's birth. By studying these ancient waves, scientists hope to learn more about how the universe evolved during its earliest and most mysterious stages. These waves remind us that the universe is never truly still. Even in regions that appear empty and quiet, invisible motions are always occurring. Space itself is constantly moving and changing, shaped by gravity and cosmic events occurring across unimaginable distances. As we continue this sleepy exploration of gravity, we begin to see that gravity is not just a force that pulls objects downward. It is also a storyteller, carrying messages across the universe through light, motion, and even the ripples of space-time itself. In the next part of our journey, we will travel to other worlds and explore how gravity feels on different planets, where weight can become lighter, heavier, or completely unfamiliar compared to Earth. As our peaceful journey through gravity continues, we begin to realize that stars themselves are born, live, and eventually die under the influence of this invisible force. Gravity is not only responsible for gathering gas and dust to create stars, but it also controls how stars shine, how long they live, and how they ultimately fade away. Stars are like enormous cosmic fires, slowly burning fuel over millions or even billions of years, with gravity constantly trying to pull their material inward while nuclear fusion inside their cores pushes outward. This delicate balance between inward and outward forces allows stars to remain stable and shine steadily across the darkness of space. When a star is first born from a collapsing cloud of gas, gravity continues compressing its core until the temperature becomes extremely high. At this point, nuclear fusion begins. During fusion, hydrogen atoms combine to form helium, releasing enormous amounts of energy in the process. This energy travels outward through the star, creating light and heat that eventually escape into space. The light from stars can travel for thousands or even billions of years before reaching distant planets, carrying with it the story of the star's past. The life of a star is determined largely by its mass. Smaller stars tend to live much longer because they burn their fuel slowly and steadily. These stars shine gently for billions or even trillions of years, glowing with a calm reddish light. Their gravity is not strong enough to compress their cores too quickly, allowing fusion reactions to continue at a slow and peaceful pace. If you could observe a small star from a distant planet, it would appear like a soft, steady lantern shining quietly in the cosmic night. Larger stars, however, live much more dramatic lives. Because they contain more mass, gravity compresses their cores much more strongly. This creates higher temperatures and faster fusion reactions, causing the star to burn its fuel at a much faster rate. These massive stars shine extremely brightly, often appearing bluish-white in color. Their brightness can be thousands of times greater than that of smaller stars, but their lives are much shorter. While small stars may live for billions of years, massive stars may only live for a few million years before their fuel begins to run out. Throughout a star's life, gravity constantly tries to pull the star inward, while fusion reactions inside the core push outward. As long as these forces remain balanced, the star remains stable. But when a star begins to run out of fuel, this balance starts to break down. The core slowly shrinks as fusion reactions slow down, allowing gravity to take control once again. When a star like our Sun begins to age, it will eventually expand into a red giant. During this stage, the outer layers of the star will slowly swell outward as the core contracts under gravity's pull. From the surface of a nearby planet, this transformation would appear like a giant glowing sphere growing larger and brighter in the sky. The star would shine with a softer reddish glow, slowly releasing its outer layers into space. These outer layers eventually drift away, forming beautiful clouds of glowing gas called planetary nebulae. These nebulae drift peacefully through space, illuminated by the remaining core of the star. What remains behind is a small, dense object known as a white dwarf. White dwarfs are incredibly dense objects where gravity has compressed stellar material into a very compact sphere roughly the size of Earth but containing the mass of an entire star. More massive stars experience even more dramatic endings. When these giant stars run out of fuel, gravity causes their cores to collapse rapidly. This collapse can trigger a massive explosion known as a supernova. Supernova explosions are among the most powerful events in the universe. For a brief moment, a single exploding star can shine brighter than an entire galaxy, releasing enormous amounts of energy and scattering heavy elements across space. These heavy elements are extremely important for the universe. Elements such as carbon, oxygen, iron, and gold are created inside massive stars during their lifetimes. When supernova explosions occur, these elements are scattered into surrounding space, eventually becoming part of new stars, planets, and even living organisms. In this way, gravity helps recycle matter across the universe, allowing new generations of stars and planets to form from the remains of older ones. If you could float through space near a dying star, the scene would be both beautiful and peaceful. Bright glowing gas clouds would drift outward slowly, illuminated by the dying star's remaining energy. Gravity would still be present, quietly shaping the motion of these clouds as they spread across space. Even after stars die, gravity continues shaping their final forms. Some cores collapse into extremely dense neutron stars, where gravity compresses matter so strongly that atoms are squeezed together into a dense sea of particles. These neutron stars can rotate rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. The most massive stars collapse even further, forming black holes, which we explored earlier in our journey. These objects represent gravity at its most extreme, where matter is compressed into an incredibly small region of space. Throughout the life of a star, gravity acts like a quiet storyteller, guiding its birth, its shining years, and its final transformation. Stars are not eternal, but their lives help create new cosmic structures. The elements formed inside stars eventually become part of planets, oceans, and even living creatures. As we continue our relaxing journey through gravity's influence, we will soon move from the life of stars to the even larger scales of the universe, where gravity gathers thousands of galaxies into enormous cosmic structures that stretch across the vast darkness of space. As we drift further into the quiet wonders of gravity, we begin to see that gravity does not only shape stars and planets, but also build structures on an unimaginably larger scale. Across the vast darkness of the universe, gravity gathers entire galaxies together into enormous cosmic communities known as galaxy clusters and superclusters. These structures are among the largest known formations in existence, stretching across hundreds of millions of light years. If you could float far above the universe and look down upon it like a cosmic map, You would see galaxies arranged in long threads and sheets, connected by invisible gravitational forces like a giant cosmic web spreading across space. In this grand cosmic structure, galaxies are not scattered randomly. Instead, they are arranged along long filaments of matter separated by vast empty regions known as cosmic voids. These voids are enormous areas of space containing very few galaxies, appearing like dark gaps between glowing threads of cosmic light. Gravity slowly pulls matter toward denser regions over billions of years, gradually strengthening these filaments and shaping the overall structure of the universe. At the intersections of these cosmic filaments, gravity gathers enormous numbers of galaxies into dense clusters. Some of these clusters contain hundreds or even thousands of galaxies moving slowly around a shared center of gravity. Within these clusters, galaxies drift like boats moving gently on a quiet cosmic ocean. Their motions are influenced not only by the gravity of individual galaxies but also by the combined gravitational pull of dark matter, which plays a mysterious but essential role in holding these structures together. Dark matter is one of the universe's greatest mysteries. It does not emit light, does not absorb light, and cannot be seen directly with telescopes. Yet scientists know it exists because of its gravitational effects. When astronomers observe the motion of galaxies inside clusters, they often find that there is not enough visible matter to explain the gravitational forces holding the cluster together. Something invisible must be providing additional mass and gravity. This unseen substance is what scientists call dark matter. If you could travel through a galaxy cluster, the experience would feel strangely peaceful. Hundreds of galaxies would drift slowly around you, their spiral shapes glowing faintly with billions of stars. Vast clouds of hot gas would float between them, heated to extreme temperatures by gravitational compression. Despite this activity, everything would move slowly on cosmic timescales, because gravity acts over enormous distances and very long periods of time. Superclusters are even larger structures. These are groups of galaxy clusters connected together along cosmic filaments. Some superclusters stretch for hundreds of millions of light years. The gravity inside these structures slowly pulls galaxies toward one another, shaping the large-scale structure of the universe over billions of years. One of the most fascinating discoveries about the universe is that gravity helped create the cosmic web shortly after the Big Bang. In the early universe, tiny fluctuations in density allowed gravity to begin pulling matter into slightly denser regions. Over billions of years, these small differences grew larger and larger, eventually forming the vast network of galaxies we observe today. Even though gravity is the dominant force shaping cosmic structures, it works slowly. The universe appears almost frozen when viewed on short time scales. But over millions and billions of years, gravity slowly reshapes everything. Galaxies move closer together, clusters form, and cosmic filaments become more defined. Inside galaxy clusters, galaxies can sometimes collide and merge. These collisions happen very slowly over millions of years. Instead of violent crashes like in movies, galaxy collisions are more like slow cosmic dances. Stars within colliding galaxies rarely collide directly because there is so much empty space between them. Instead, gravity gradually pulls galaxies together, mixing their stars into new, larger galaxies. These mergers are important for the evolution of galaxies. When galaxies collide, their gas clouds can compress, triggering new waves of star formation. This allows gravity to continuously recycle matter and create new generations of stars across the universe. Gravity also helps scientists measure the total mass of galaxy clusters. By studying how galaxies move inside clusters and how light bends around them, astronomers can calculate how much invisible mass must be present. This has helped confirm the existence of dark matter halos surrounding most galaxies and clusters. If you could watch the universe from a distance over billions of years, you would see gravity slowly pulling matter together into increasingly complex structures. The universe would look like a slowly evolving cosmic ecosystem, where gravity acts as the invisible architect. Even though the universe is expanding, gravity continues to pull matter locally together. This creates a fascinating balance between expansion and gravitational attraction. On very large scales, space continues to stretch, but within galaxies and clusters, gravity keeps matter bound together. As we continue our calm exploration, we move closer to one of the universe's most mysterious subjects, dark matter. In the next part of our journey, we will explore how this invisible substance shapes galaxies and influences the structure of the entire cosmos, even though it cannot be seen directly. As our calm cosmic journey continues, we reach one of the most mysterious and silent secrets of the universe, dark matter. This strange substance cannot be seen with telescopes, cannot be touched, and does not interact with light the way normal matter does. Yet gravity reveals that dark matter must exist, because without it, galaxies and galaxy clusters would not hold together the way they do. Imagine floating quietly through deep space, surrounded by glowing stars and faint galaxies. Everything appears peaceful, but hidden within that peaceful darkness is something invisible, quietly shaping the movement of stars and cosmic structures. For many years, astronomers noticed something strange when observing galaxies. Stars near the outer edges of galaxies were moving much faster than expected. According to the laws of gravity, stars farther from the center of a galaxy should move more slowly because the visible mass of stars and gas is concentrated near the middle. But observations showed that outer stars were moving at nearly the same speed as inner stars. This meant that there must be additional unseen mass providing extra gravitational pull. Scientists began calling this unseen mass dark matter. Dark matter does not behave like normal matter. Normal matter is made of atoms, which interact with light, heat, and electromagnetic forces. Dark matter, however, seems to interact only through gravity. It does not emit light or absorb light, making it completely invisible to direct observation. Scientists can only detect dark matter by studying how its gravity affects visible matter and light traveling through space. If you could observe a galaxy containing dark matter from far away, you would not see the dark matter itself. Instead, you would see its gravitational effects. Stars would move faster than expected, galaxy shapes would remain stable despite their rotation, and light from distant objects would bend more strongly when passing through regions filled with dark matter. In this way, dark matter acts like an invisible scaffold holding galaxies together. Dark matter is thought to form enormous halos surrounding galaxies. These halos extend far beyond the visible stars and gas clouds. Although galaxies appear to be glowing disks of light, most of their mass may actually be hidden within these invisible halos. Gravity from dark matter helps keep galaxies from flying apart as they rotate through space. Without dark matter, the universe might look very different. Early galaxies might not have formed as quickly after the Big Bang. Gravity would have had less material to work with when building cosmic structures. Some scientists believe dark matter played a crucial role in helping the first galaxies form by providing additional gravitational attraction during the early universe's evolution. Scientists have not yet directly detected dark matter particles in laboratories, but many experiments are searching for them. Researchers use underground detectors, particle accelerators, and space telescopes to look for clues about what dark matter might be made of. Some theories suggest dark matter could be made of exotic particles that rarely interact with normal matter. If you could travel through a region of space dominated by dark matter, you would not feel anything unusual. Dark matter does not push or pull directly on objects the way electromagnetic forces do. Instead, you would simply notice its presence through the way nearby stars and galaxies move. The experience would feel like drifting through a quiet cosmic ocean where invisible currents shape the motion of everything around you. Dark matter also plays an important role in galaxy clusters. The combined gravity of dark matter and visible matter helps hold clusters together. Without dark matter, galaxy clusters might slowly drift apart over time. Instead, dark matter keeps these massive structures stable for billions of years. Even though dark matter is mysterious, it is believed to make up a large portion of the universe's total mass. Scientists estimate that only a small percentage of the universe is made of the matter we can see. The rest is divided between dark matter and another mysterious component called dark energy, which is responsible for the accelerating expansion of the universe. Together, these unseen forces shape the long-term future of cosmic evolution. dark matter reminds us that the universe still holds many secrets. Even with modern technology and advanced telescopes, there are still invisible structures influencing everything we observe. Gravity continues to act as a bridge between the visible and invisible parts of reality, helping scientists uncover hidden cosmic mysteries. As we drift deeper into our sleepy exploration, we move toward another fascinating topic, gravitational lensing in greater detail, where gravity not only reveals hidden matter but also allows us to see deeper into the history of the universe by bending light from ancient galaxies. In the next chapter, we will explore how gravity can act like a natural telescope, allowing us to look far back in time toward the birth of the first galaxies. As we continue floating peacefully through the universe of gravity's mysteries, we return once again to one of its most beautiful and useful effects, gravitational lensing. This phenomenon shows us that gravity can act like a natural telescope, bending and magnifying light from distant galaxies so that we can see deeper into space and farther back in time. Imagine drifting slowly through a dark cosmic ocean, where distant stars and galaxies shine faintly like lanterns scattered across endless night. As their light travels toward us, it must pass through regions of space where massive objects like galaxies or galaxy clusters are waiting. When that light crosses these regions, gravity gently bends its path, like light passing through the curved surface of a glass lens. Gravitational lensing happens because massive objects warp space-time around them. According to modern physics, space is not empty and rigid. Instead, it behaves like a flexible fabric that can be stretched or curved by mass. When a massive object sits in space, it creates a dip in this fabric. Light traveling through space always tries to follow the straightest possible path, but when space is curved, the straightest path becomes curved as well. As a result, light beams bend around massive objects rather than traveling in perfectly straight lines. If you could observe this effect with your own eyes through a powerful telescope, you might see strange and beautiful patterns. Distant galaxies located behind a massive galaxy cluster may appear stretched into long glowing arcs of light. Sometimes, the light bends so perfectly that it forms a complete circle around the massive object. These glowing circles are known as Einstein rings, named after the scientist whose theories predicted this phenomenon long before it was observed. Gravitational lensing is extremely useful for astronomers. It allows scientists to observe galaxies that would otherwise be too faint or too distant to detect. Some of the most distant galaxies ever discovered were found using gravitational lensing, because the gravitational field of a foreground galaxy cluster acted like a magnifying glass, making distant objects appear brighter and larger. There are different types of gravitational lensing. Strong lensing occurs when the gravitational field is extremely powerful, such as near galaxy clusters or supermassive black holes. This type of lensing produces dramatic visual distortions, including arcs, rings, and multiple images of the same distant galaxy appearing in different locations in the sky. Weak lensing is much more subtle. It slightly distorts the shapes of galaxies without producing obvious visual patterns. By carefully studying these tiny distortions, scientists can map the distribution of dark matter across the universe. Gravitational lensing also helps scientists study dark matter. Since dark matter does not emit light, it cannot be seen directly. However, its gravity still bends light passing through regions where dark matter is present. By measuring how light is bent, scientists can create maps showing where dark matter must be located. These maps often reveal invisible halos of dark matter surrounding galaxies and clusters. If you could travel through a region of space where gravitational lensing is strong, the sky would look very unusual. Distant stars might appear stretched into glowing streaks. Some stars might appear multiplied, showing several images of the same star in different places. The shapes of galaxies behind massive objects would look warped and curved, like reflections in a rippling pond. Gravitational lensing also allows scientists to study the early universe. Because light takes time to travel across space, looking at very distant galaxies is like looking back in time. The light from distant galaxies may have traveled for billions of years before reaching Earth. By studying these ancient light sources, astronomers can learn what the universe looked like when it was much younger. Some gravitational lenses are so powerful that they can reveal objects that formed shortly after the Big Bang. These observations help scientists understand how the first stars and galaxies formed. Without gravitational lensing, many of these ancient cosmic objects would remain hidden from our view. Gravitational lensing is not only a scientific tool but also a beautiful cosmic phenomenon. The bending of light creates artistic patterns across the sky, showing how gravity can shape not only matter but also the way we perceive the universe. In a sense, gravity is not just building structures in space, it is also painting pictures with light. Even black holes can act as gravitational lenses. Light passing very close to a black hole can be bent into circular photon rings around the event horizon. Some of the most famous black hole images captured by astronomers show these bright rings surrounding dark shadows, demonstrating how powerful gravity can be in extreme environments. As we continue our calm exploration of gravity, we move closer to understanding how gravity can also create waves in space-time itself. In the next chapter, we will return to gravitational waves and explore how these cosmic vibrations carry messages from the most powerful events in the universe. As our peaceful cosmic journey continues, we return to one of the universe's most subtle and poetic phenomena, gravitational waves. These invisible ripples move through the fabric of space-time like soft waves traveling across a calm, endless ocean. They are created when massive objects move violently or collide with enormous energy. Yet by the time these waves reach Earth, they are incredibly weak, passing through everything around us without causing any noticeable disturbance. You could be sitting quietly, reading under soft light, and a gravitational wave could pass through your body, the building around you, and the entire planet without you ever feeling it. Gravitational waves were first predicted by modern physics when scientists realized that gravity was not just a force pulling objects together, but also a geometric property of space-time. When massive objects accelerate or change motion suddenly, they disturb space-time, creating ripples that travel outward at the speed of light. Imagine throwing a stone into a still, calm lake. The stone creates ripples that spread outward in circular waves. In a similar way, gravitational waves spread outward through space when powerful cosmic events occur. The strongest sources of gravitational waves come from some of the most dramatic events in the universe. When two black holes orbit each other, they slowly lose energy by emitting gravitational waves. Over millions of years, this energy loss causes them to spiral closer together. At first, their motion is slow and graceful, like two dancers circling each other in a quiet cosmic ballet. But as they move closer, their speed increases and the gravitational waves they emit become stronger. Eventually, the black holes collide in a final explosive moment. Although no light escapes directly from the collision, the event releases an enormous amount of gravitational wave energy. For a brief moment, the power released by merging black holes can exceed the total brightness of all the stars in the observable universe combined. This energy travels outward as ripples in space-time, carrying information about the mass, speed, and motion of the colliding objects. Detecting gravitational waves on Earth required extremely advanced technology. Scientists built large laser-based detectors designed to measure incredibly small changes in distance. These detectors contain long vacuum tunnels where laser beams bounce back and forth between mirrors. When a gravitational wave passes through, it slightly stretches space in one direction while compressing it in another. These changes are so small that they are smaller than the width of a proton, yet scientists can still measure them using precise instruments. The first direct detection of gravitational waves marked a historic moment in science. It confirmed predictions made decades earlier and opened a new way for astronomers to study the universe. Instead of only observing light, scientists could now listen to the invisible vibrations of space-time itself. This new field of science is sometimes called gravitational wave astronomy. Gravitational waves can carry information from regions of the universe that are otherwise impossible to observe. Some events do not produce visible light, especially when black holes collide. Before gravitational wave detection became possible, these events were hidden from human observation. Now scientists can study them through the waves they produce. If you could float far away in deep space, You might think the universe would be completely still and silent. But gravitational waves would still be passing through, gently stretching and squeezing space around you like soft breathing motions of the universe. These waves do not cause destruction. Instead, they move peacefully through matter, carrying information across billions of light years. Gravitational waves also help scientists study the early universe. Some theories suggest that gravitational waves were created during the first moments after the Big Bang. These primordial waves could contain information about how the universe expanded and evolved during its earliest stages. Detecting these ancient waves is extremely difficult, but scientists continue searching for them using advanced space-based detectors. Gravitational waves remind us that the universe is always moving, even in places that appear completely empty. Space itself is dynamic and alive with motion on cosmic scales. Stars move, galaxies collide, black holes merge, and space-time itself vibrates with energy traveling across the universe. As we continue our sleepy exploration of gravity, we move toward another fascinating chapter: how gravity shapes the life cycles of planets beyond Earth. In the next part of our journey, we will explore how gravity feels on different worlds, where it can be lighter, heavier, or completely strange compared to what we experience on Earth. As we continue drifting through our peaceful cosmic story, we travel closer to the idea that gravity is not the same everywhere in the universe. Gravity changes depending on the mass and size of a planet or celestial body. This means that if you could stand on different planets, you would feel very different levels of weight. Some worlds would make you feel lighter, allowing you to jump higher and move more freely, while others would make you feel extremely heavy, as if an invisible force were gently pressing you toward the ground. Gravity is not just a universal rule, it is also a local experience that changes from world to world. On smaller planets and moons, gravity is weaker because there is less mass pulling objects toward the center. Imagine standing on a small moon floating quietly in space. When you jump, you would rise much higher and stay in the air longer before slowly drifting back down. Movements would feel almost dreamlike, as if you were walking through slow motion. Some astronauts have experienced this sensation when exploring the moon, where gravity is about 1/6 as strong as it is on Earth. Every step would feel lighter, and even small pushes could send you floating upward. On larger planets, gravity becomes stronger. Massive planets have more material pulling inward toward their centers. If you could stand on a gas giant planet, you would feel extremely heavy, as if gravity were gently pulling you down with great strength. Walking would be very difficult, and standing upright might feel exhausting. These planets are not solid surfaces like Earth, but are made mostly of thick layers of gas and liquid compressed under enormous pressure. Earth itself has a comfortable level of gravity that allows life to move, grow, and evolve easily. Plants can grow upward towards sunlight, animals can move across land, and oceans can remain liquid. Earth's gravity is strong enough to hold our atmosphere in place, but not so strong that movement becomes difficult for living creatures. This balance has helped life flourish over millions of years. If you traveled to Mars, you would experience about 1/3 of Earth's gravity. You could jump much higher and lift heavier objects more easily. However, Mars has a much thinner atmosphere than Earth, so although you might feel lighter, you would need special equipment to breathe. The Martian landscape would feel quiet and still, with dust drifting slowly across the red surface under weak gravity. Venus, on the other hand, has gravity very similar to Earth's. If you could stand on its surface, you would feel nearly the same weight as you do on Earth. But Venus is an extremely hostile environment due to its thick, hot atmosphere and crushing pressure. Gravity alone does not determine whether a planet is habitable. Temperature, atmosphere, and chemical conditions are also important for supporting life. Gas giants such as Jupiter have much stronger gravity because of their enormous mass. If you could somehow stand on Jupiter's cloud tops, you would feel much heavier than on Earth. Jupiter's gravity is so strong that it can influence the orbits of nearby asteroids and comets, sometimes pulling them into new paths through the solar system. This gravitational influence helps protect inner planets from some cosmic impacts, acting like a gravitational shield in some cases. If you visited the outer regions of the solar system, you would encounter smaller icy worlds with extremely weak gravity. on these distant objects, you could potentially jump high into space with little effort. However, because gravity is weak, these worlds cannot hold thick atmospheres, making them cold and airless. Gravity also influences how planets form. During the early solar system, gravity pulled dust and gas together into larger and larger bodies. This process determined how big planets became and what materials they contained. Rocky planets formed closer to the sun, where heat prevented lighter gases from staying nearby, while gas giants formed farther out where temperatures were colder. If you could travel across many different planets, gravity would feel like a changing musical rhythm across the universe. Some worlds would feel heavy and slow, while others would feel light and free. Gravity shapes not only the physical structure of planets, but also how life and movement evolve on their surfaces. As we continue our calm journey through gravity's wonders, our next chapter will explore what it would feel like to live in low-gravity environments, such as space stations and long-term space habitats, where humans must adapt to life without Earth's familiar gravitational pull. As we continue our peaceful journey through the wonders of gravity, we move closer to understanding what life would feel like in environments where gravity is very weak. Low gravity does not only change how objects move, it also changes how the human body behaves, how water flows, how fires burn, and how daily life itself would feel. Imagine floating gently inside a quiet space station, drifting slowly through soft lighting while looking down at Earth glowing beautifully in the distance. In this environment, nothing feels heavy. Instead, movement becomes smooth and slow, like floating through a calm dream. Astronauts who spend time in space experience low gravity, often called microgravity. In this state, objects and people do not truly become weightless. Gravity is still pulling everything toward Earth, but because the spacecraft and everything inside it are falling around Earth together at the same speed, objects appear to float. This creates a strange and peaceful sensation where movement requires small, careful pushes. If you let go of a tool in space, it will simply float beside you until you catch it again. Living in low gravity changes how the human body works over time. On Earth, gravity helps keep bones strong because bones must constantly support body weight. In low gravity, bones do not need to support as much force, which can cause them to slowly lose density if astronauts stay in space for long periods. To prevent this, astronauts must exercise regularly inside space stations using special equipment that simulates physical resistance. Without exercise, muscles could weaken because they are not working against strong gravitational pull. The heart and blood circulation system also adapt to low gravity. On Earth, gravity helps pull blood toward the lower parts of the body. In space, blood can shift upward more easily, sometimes causing astronauts' faces to appear slightly puffy. Over time, the body adjusts to this new environment, but returning to Earth's gravity can feel uncomfortable until the body readjusts. Even simple actions like drinking water become different in low gravity. Water does not naturally flow downward into a cup. Instead, it forms floating spheres of liquid that must be carefully controlled using special containers. Without proper tools, liquids could spread across the air inside a spacecraft, creating floating droplets that move slowly through the cabin. Fire also behaves differently in low gravity. On Earth, flames rise upward because hot air is lighter than cold air. In space, flames become more spherical and burn more slowly because there is no strong upward airflow. Scientists study these low-gravity flames to better understand combustion and improve safety systems for space travel. Sleeping in low gravity can also feel unusual. Astronauts usually sleep inside special sleeping bags attached to walls to prevent them from floating around the spacecraft. Without being secured, a sleeping person could drift slowly through the cabin. Despite these differences, many astronauts report that space sleep can feel very peaceful and quiet because there are fewer disturbances compared to Earth. Plants can also grow in low gravity, but they behave differently. On Earth, plant roots grow downward because gravity guides them towards soil moisture, while stems grow upward toward sunlight. In space, plants must rely more on light direction rather than gravity to determine growth patterns. Scientists study plant growth in space to prepare for future long-term space missions where humans may need to grow their own food. Long-term living in low-gravity environments presents many challenges. Human bodies evolved on Earth under constant gravitational force. When gravity is reduced for long periods, the body begins adapting in ways that can be uncomfortable when returning to Earth. This is why astronauts must undergo careful training before and after space missions. Future space habitats may use artificial gravity to solve these problems. By rotating large space stations, scientists can create centrifugal force that simulates gravity. Inside these rotating habitats, people would feel a gentle pull toward the outer walls, similar to standing on a curved surface. This could allow humans to live comfortably in space for long periods while protecting their health. If humanity ever builds large colonies in space, gravity will become an important design factor. Architects and engineers will need to consider how gravity affects movement, health, and daily life. Cities in space might look very different from cities on Earth, with curved corridors and rotating living spaces designed to simulate natural gravity. Low-gravity environments remind us that gravity is not only a cosmic force shaping stars and planets, but also a force that shapes how living beings experience their world. Gravity influences biology, technology, and even human behavior in subtle ways. As our relaxing exploration continues, we will soon travel to the edge of the universe itself, where gravity becomes weaker and weaker as space expands, and where the fate of the cosmos is shaped by the mysterious force driving the universe apart. In the next chapter, we will explore the expanding universe and the role of gravity in cosmic destiny. As our calm cosmic journey continues, we travel farther from stars, planets, and galaxies, moving into the deepest, quietest regions of the universe. In these vast spaces between galaxies, gravity becomes extremely weak, yet it never truly disappears. Even in the most empty parts of space, invisible gravitational connections still exist, gently influencing the motion of distant cosmic objects. Imagine drifting slowly through endless darkness where stars are only faint glimmers far away, like soft sparks fading into the distance. Space here feels peaceful and still, yet beneath this stillness, the universe is constantly expanding and evolving. In deep space, the gravitational pull from nearby stars and galaxies becomes very weak because gravity decreases with distance. The farther you move from a massive object, the weaker its gravitational influence becomes. However, because the universe is so massive, even distant galaxies can still exert tiny gravitational forces across enormous distances. These weak forces help maintain the large-scale structure of the universe, keeping cosmic filaments and galaxy clusters loosely connected over billions of years. At the same time, another powerful force is at work across the universe: the expansion of space itself. Since the Big Bang, space has been stretching outward, carrying galaxies away from each other. This expansion is not caused by galaxies moving through space, but rather by space itself expanding like the surface of an inflating balloon. As space expands, galaxies become farther apart over time, especially in the most distant regions of the universe. Scientists discovered that the expansion of the universe is actually accelerating. This means galaxies are moving away from each other faster and faster as time passes. The mysterious force responsible for this acceleration is called dark energy. While gravity tries to pull matter together, dark energy pushes space apart, creating a cosmic balance between attraction and expansion. If gravity is the cosmic glue holding structures together, dark energy is like a gentle pressure pushing the universe outward. In regions far from galaxies, dark energy begins to dominate over gravity. This is why distant galaxies appear to be moving away from us at increasing speeds. Over extremely long time scales, this could change the appearance of the universe dramatically. Some theories suggest that distant galaxies may eventually become so far away that their light will never reach us, leaving future observers surrounded by a much emptier cosmic sky. If you could travel to the far edge of gravitational influence around galaxies, the experience would feel very quiet. You would drift slowly through space with very little gravitational pull from nearby objects. Motion would feel effortless, as even small pushes could send you drifting for long distances before stopping. However, you would also need to be careful, because without strong gravity to hold objects together, navigation would become difficult. Deep space also contains vast clouds of extremely thin gas and dust. Gravity is often too weak in these regions to pull this material into stars or planets. Instead, these clouds remain spread across enormous distances, slowly moving through space like faint cosmic fog. Over billions of years, gravity may eventually gather some of this material into new star systems, continuing the cosmic cycle of birth and death. Even though gravity is weak in deep space, it still plays a role in guiding the motion of spacecraft traveling through the solar system. Space missions often use gravitational fields from planets and moons to change direction and speed without using extra fuel. By carefully planning trajectories, scientists can use gravity like a natural navigation tool, helping spacecraft reach distant destinations efficiently. If you could look at the universe from a very great distance, you would see gravity and expansion working together in a delicate balance. Gravity pulls matter inward, forming stars, galaxies, and clusters. Meanwhile, cosmic expansion pushes matter outward, spreading galaxies farther apart. This balance will shape the future of the universe over trillions of years. In the most extreme future scenarios, some scientists believe the universe could continue expanding until even atoms begin to drift apart, though this remains a theoretical possibility. Other theories suggest gravity might eventually slow or change the expansion. The long-term fate of the universe remains one of the greatest mysteries in science. Deep space reminds us that even when things appear completely empty, forces like gravity and dark energy are still quietly shaping reality. The universe is never truly still. It is always moving, expanding, and evolving under the influence of these cosmic forces. As we approach the final chapters of our sleepy gravity journey, we will soon explore the future of gravity research and what scientists hope to discover about this mysterious force in the coming centuries. In the next chapter, we will look at how gravity research may help humanity explore new worlds and understand the deepest secrets of the cosmos. As our peaceful cosmic journey approaches its later chapters, we look toward the future of gravity itself and how humanity will continue studying this mysterious force. Gravity has already revealed many of its secrets, from shaping galaxies to bending light, creating black holes, and guiding the motion of planets. Yet scientists believe there is still much more to learn. Future discoveries may change how we understand space, time, energy, and even the origins of the universe. Imagine standing on the edge of tomorrow's science, looking into a quiet future where new technologies slowly unlock deeper layers of cosmic knowledge. One of the biggest goals of future gravity research is to unite gravity with the other fundamental forces of nature. Currently, gravity is described by the theory of general relativity, which explains gravity as the curvature of spacetime. However, the other fundamental forces, electromagnetic force, strong nuclear force, and weak nuclear force, are explained using quantum physics. Scientists are still searching for a unified theory that can describe both gravity and quantum physics together. Such a theory is sometimes called a theory of everything. Understanding gravity at the quantum level is one of the greatest challenges in modern physics. At extremely small scales, gravity appears much weaker than other forces. Scientists believe that studying gravity at quantum scales may reveal new particles or hidden dimensions of space. Some theories suggest that gravity might spread into extra dimensions that are too small for us to detect directly. If this is true, it could help explain why gravity is so weak compared to other fundamental forces. Future telescopes and space observatories will help scientists study gravity across greater distances than ever before. These instruments will be able to detect faint signals from the early universe and observe gravitational waves from extremely distant cosmic events. By studying these signals, scientists hope to learn more about how the universe formed and how gravity influenced its early evolution. Space-based gravity experiments may also become more advanced. Scientists are already designing missions that can measure tiny variations in gravitational fields around Earth and other planets. These measurements help improve navigation systems, climate models, and our understanding of Earth's internal structure. Gravity measurements from space can even help scientists map underground water reserves and monitor changes in ice sheets caused by climate variations. Human space exploration will also depend heavily on understanding gravity. Future missions to the Moon, Mars, and beyond will require better knowledge of how low-gravity environments affect human health and engineering systems. Scientists are already developing technologies that could create artificial gravity for long-duration space travel. Rotating space habitats may allow humans to live comfortably in space by simulating Earth-like gravity. Another exciting area of gravity research involves black holes. Scientists are still trying to understand what happens inside black holes beyond the event horizon. Current physics cannot fully describe conditions near the singularity, where gravity becomes extremely intense and space-time may break down. Future theories may help reveal what truly happens inside these mysterious regions. Some researchers are also studying how gravity might be used as a tool for advanced technology. In the distant future, humanity might develop technologies that manipulate gravitational fields for propulsion or energy generation. Although this is purely theoretical today, it represents an exciting possibility for future scientific discovery. Astronomy will continue using gravity as a tool for exploring the universe. Gravitational lensing will help scientists study distant galaxies and map dark matter more accurately. New gravitational wave detectors in space may allow scientists to detect collisions between black holes and neutron stars across the universe with incredible precision. Future research may also help solve mysteries about dark matter and dark energy. Scientists are still trying to determine what dark matter is made of and why dark energy is causing the universe's expansion to accelerate. Solving these mysteries could completely change our understanding of physics and cosmology. Gravity research may even help humanity understand its own origins. By studying the early universe, scientists can learn how gravity helped form the first stars, galaxies, and planetary systems. This knowledge may help us understand how rare or common life might be across the cosmos. As technology advances, gravity research will likely become more precise, allowing scientists to measure extremely small gravitational effects that were once impossible to detect. These discoveries may reveal new physics beyond our current understanding. The future of gravity research feels like standing quietly at the edge of a vast cosmic ocean, watching new waves of knowledge slowly arrive. Each discovery builds upon the last, helping humanity understand the universe in deeper and more meaningful ways. As we approach the final chapter of our sleepy gravity story, we will reflect on gravity's role as the force that holds the universe together, from the smallest particles to the largest cosmic structures. In the final section, we will explore gravity's gentle legacy across the entire cosmos. As we reach the final chapter of our peaceful journey through gravity, we take a moment to look back across the vast cosmic story we have explored. Gravity has been present from the very birth of the universe to the formation of stars, galaxies, planets, oceans, life, and even human civilization. It is a silent architect, patiently shaping the structure of everything we see and everything we cannot see. Imagine drifting slowly through deep space, looking back at glowing galaxies scattered like soft lights across endless darkness. Each one exists because gravity gathered matter together over billions of years, turning chaos into structure and darkness into light. Gravity began shaping the universe almost immediately after the Big Bang. In the earliest moments of cosmic history, matter and energy were spread nearly evenly across space. But tiny differences in density allowed gravity to slowly pull matter into thicker regions. Over time, these regions grew larger, forming stars, galaxies, and clusters of galaxies. Without gravity, the universe would remain a thin, scattered cloud of particles, never forming complex structures capable of supporting life. Gravity is also responsible for the beauty and stability of planetary systems. Planets orbit stars because gravity balances motion with attraction, allowing worlds to travel in endless cosmic cycles. Moons orbit planets, and planets orbit stars, creating elegant patterns of motion that have continued for billions of years. This stability has allowed life to evolve on Earth under relatively calm and predictable conditions. On Earth, gravity is deeply connected to life itself. It keeps oceans in place, allows rivers to flow, shapes weather systems, and helps maintain the atmosphere that protects living organisms. Without gravity, water would drift into space, air would escape, and life as we know it would not exist. Gravity is therefore not just a cosmic force, but also a life-supporting force. Gravity also shapes the life and death of stars. Inside stars, gravity constantly pulls matter inward while nuclear fusion pushes outward. When this balance ends, stars change into new forms: white dwarfs, neutron stars, or black holes. Through these transformations, gravity helps recycle matter across the universe, ensuring that old stars contribute to the birth of new ones. On the largest cosmic scales, gravity forms the vast cosmic web of galaxies connected by invisible filaments of matter. Even though dark matter remains mysterious, its gravitational effects help hold galaxies and clusters together. Gravity acts like an invisible glue holding the universe's structure in place while cosmic expansion slowly stretches space itself. Gravity also influences time and space. Massive objects can slow the passage of time and bend the path of light. This means that gravity does not simply pull objects together, it also changes the very nature of reality. Near massive objects like black holes, gravity becomes so strong that space-time itself becomes extremely distorted. Humanity has learned to work with gravity rather than simply fight against it. Rockets use physics to escape Earth's gravity, while spacecraft use gravitational assists to travel across the solar system. Future space exploration will rely even more on understanding gravity to build space habitats, travel to distant planets, and explore deeper regions of the universe. Despite all we have learned, gravity still holds many mysteries. Scientists continue searching for ways to unify gravity with quantum physics, understand dark matter and dark energy, and explore gravity's role in the earliest moments of the universe. Each new discovery reveals that gravity is both simple and deeply complex at the same time. In a quiet, philosophical sense, gravity can be seen as the universe's storyteller. It connects everything across space and time. It shaped the stars that created the elements inside our bodies. It formed the planet we live on. It controls the motion of galaxies that stretch across billions of light years. In this way, gravity is not just a physical force. It is a cosmic bridge linking the past, present, and future. As we end this journey, imagine drifting peacefully through the universe, surrounded by soft, glowing stars. Gravity continues working silently, holding everything together in a grand cosmic harmony. Though invisible, it is always present, gently guiding the dance of the universe across eternity. And so our sleepy science story about gravity comes to a calm and peaceful end, leaving behind a universe still moving, still expanding, and still held together by the gentle pull of gravity.